This is part 2 of the video podcast for Chapter 3 on basin scale force water balance. In part 1, I introduced the concept of an energy balance and how we use that to estimate water and energy fluxes, especially energy fluxes, for evaporation at the watershed scale. I also provide a conceptual understanding of evaporation and transpiration, including how we can use sap flow to estimate transpiration directly. Now what I want to do is look at evapotranspiration as a whole, especially when you're coming off a canopy that might be an individual tree, it might be a canopy of mixed individuals of the same population, same species, mixed populations from mixed species, a whole watershed or possibly even a whole region, depending on what you need to compute. Now, this is not intended to be an introduction to evaporation or even evapotranspiration. That would have to come from a class on Introduction to Physical Hydrology. So the ideas here are going to try to focus specifically on evapotranspiration in an ecohydrologic context. And to do that, we're going to focus on one equation, but it is a doozy. I have to warn you. It's called the Penmen-Monteith equation. And what I'm going to do is present the equation, the concepts behind it, and the terms that are in it, and then illustrate some of the aspects of that equation and how well it works. The first thing is that we have to have a common basis for understanding what's happening with water when it evaporates. So you already know that if you begin with dry air and you apply a fixed temperature as shown in this beaker in the upper left, that inevitably some of the molecules of the water at the water surface will randomly move into the air. We call that movement evaporation. More and more will accumulate in the air. Some of them will randomly go back down in the water, but proportionally more will be coming out because the air is relatively dry than is going in. And so over time, we'll see on this pressure gauge a change from the baseline pressure of dry air. It's not zero, it's just the baseline pressure of dry air, and it's going to increase. So going to the right here, clockwise, indicates an increase in pressure. And that's happening because we have water vapor in the air, which means that the pressure of the air is going up. When we talk about that pressure in terms of the part that's induced by water, we can call that the partial pressure due to due to water. And by partial pressure, we mean the difference between what you see in this gauge versus this gauge. So this is the pressure associated with dry air, and then the difference between this total pressure and this baseline pressure in dry air is the partial pressure of that water. Because that water is in a vapor state, we can use the term vapor pressure. So vapor pressure is another way of saying the amount of water present in a given volume of air. And because it's given as a pressure, pressure has the units of a force per unit area. So you might think of that as a mass, but remember, force consists of mass as well. Okay, so over time, as we sit at a fixed temperature, we'll accumulate more and more water vapor, and eventually we'll reach a point, which is shown in the lower left, where we have as many individual molecules of water going from the air into the water as went from the water into the air. And so we have this equilibrium balance between how much is coming out of the water and how much is going in. And at that moment, we have the term saturation. Now, saturation is really an ideal because, of course, at any moment in time, you might have more particles in the air than it would normally be able to hold, so that it is going to be fluctuating around. But there is this idea of a saturation. So for any given temperature, there is a maximum amount of water that the air can hold as vapor, and that's the saturation vapor pressure. If we increase the temperature, here going from 20 degrees Celsius to 30 degrees Celsius, we can hold significantly more. Why does that happen? Because we're putting more energy into the system. That means more water molecules are going to be bouncing around, and more of them are going to be able to escape the water and hang out in the air. And so you can see the amount of water in this case has gone down. What would be nice to know is the relationship between temperature and saturated vapor pressure, and I'm going to show that to you in a few moments. but there is a curve. This is just illustrating 2 points on that curve for 20 and 30 degrees Celsius. But there is, in fact, a curve that on the x-axis is temperature, on the y-axis is vapor pressure. Okay, so this basically just goes to the general idea that you might have that if air is dry, it can hold more water, and that's the key thing. And then how much water the air can hold is governed by the saturation vapor pressure at that temperature. Okay, so without further ado, here's the Penmen-Monteith equation. Now I know this looks pretty scary to many of you. Some of you maybe have not even taken a hydrology class before. It's day number 2. You're looking at this equation and you're thinking, what did I get myself into? What am I doing here? But please be patient, because I assure you that what is on this screen is understandable, and I will go through it. But more importantly, this all comes from basic physics focusing on mass conservation and fundamental principles of how water and temperature work, or water and heat, how they work. Now, I'm not going to go through a derivation of this equation. I know many of you, I'm sure, wish that I would go through such a derivation, but I'm not going to. However, if you would like to see that derivation, I do have it written down, and I would be happy to share that with you. Now, if you remember from part 1 video podcast, I showed you the energy balance. The energy balance had 4 terms: net radiation, sensible heat, latent heat, and conduction, or subsurface heat. Okay, so 3 of those you can see explicitly here. On the left, we have the evaporation term. E is evaporation in terms of mass, right? Mass, or rate of evaporation mass, so kilograms of water per square meter of ground per second. L, remember, that's the latent heat of vaporization of water. It converts from that mass to an energy, so that LE combined is the energy that's lost through evaporation through time. Notice here that we can specify the latent heat of vaporization as a function of the water temperature, usually near the surface of the water, and there's a simple function here I'm not going to go into. It's pretty easy. Net radiation, something you can just directly measure. We've talked about that before. G, that's the conductive heat flux, so you can measure that with a subsurface heat plate. I showed that before. Let's look at some of the other simple things in this equation. Rho, this is the variable for density. It's a Greek symbol, and with the subscript A, this is rho A. That A is for air, W is for water, with all the subscripts. So rho A is the density of air. And the density of air here, kilograms of air per cubic meter of air, is given here these different values at these different temperatures, just to illustrate those values. I'm sure you can find a large lookup table or an estimation equation online if you want one. So that's pretty simple. CP, heat capacity of air, we've already talked about that. I just give you a sample value here. You can look up more on the internet. Now we come to the things that are new. A triangle, which is delta. We have RS, RA. We have a gamma, Greek symbol gamma. We have this, looks like a V with a lowercase a, but it's actually the Greek symbol nu, and it even has a star. And star usually means saturation related. So let's start up here with nu A star minus nu A. What's this? Well, nu A is the vapor pressure in the air. It's kind of convenient. If you think of V and vapor, then that's how much is in the air, and VA star is the saturation vapor pressure. So I've already shown you, if we go back one, saturation vapor pressure is indicated by this lower left beaker. The vapor pressure at any moment in time is shown in the upper right, and so typically on any given moment we have less vapor in the air than can be held given that temperature. And so that difference there, that vapor pressure difference or vapor pressure gradient, or even vapor pressure deficit, as some people call it, that's a huge driver. So let's look at all these variables. Okay, as the density of air goes up, we have higher evaporation rates. As the heat capacity goes up, we have higher evaporation rates. As this gradient goes up, we also have higher evaporation rates. So the air can hold more water in those circumstances. Okay, now let's look at a few other variables. Let's see, we've covered, oh yeah. The next simple one here is gamma. Gamma is the psychrometric constant, not psycho, psych rho. And there's a big difference here because we're not talking about psychology. What this has to do is it relates the partial pressure of water, in other words, the vapor pressure, to the temperature and altitude that we're at. So you can imagine that if you're in the atmosphere, as you go higher and higher up, then there is a greater and greater capacity to hold water, and so evaporation would go up. And you can see that in this relationship. So atmospheric pressure is the pressure at the given altitude that you're at. So as you go higher in the air, that pressure is going down. As pressure goes down, gamma goes down. And if gamma goes down and it's in the denominator, then evaporation goes up, because this shows an inverse relationship between LE and gamma. Okay, so that's how the psychrometric constant works. It's a function of altitude ultimately. And you can see it's essentially the water change per unit temperature that's there. Okay, so now let's move on to the next few terms. So what about this delta? Okay, delta is, looks like a beast because it's this funny symbol, and in turn, it is governed by an equation that looks tricky. But actually, it's a relatively simple concept. On the lower right here is the promised relationship I mentioned, which is the relationship between vapor pressure and temperature. The main solid line here shows that function. I call it the saturation function. So at any given temperature, when you hit that line, the vapor pressure is at the saturation level. There is a small deviation here if you're going from vapor to ice, but that's not important right now. If you're below this line, it means that the air can hold more moisture than that. And if you're above this line, then it means that you're oversaturated and you're going to lose some. What delta is it's the slope of this line. And, well, actually, because this isn't a line, this is a function. And depending on where you are, you have a different capability there. So you can imagine at a very high temperature, you can see there's a very steep gradient. The saturation vapor pressure is quite high, so there's a lot of potential to hold water. At the same time, the amount of moisture, at the air-water interface might also be relatively high too, and so then this gradient could be relatively low. So the tricky thing about delta is that it occurs in both the numerator and the denominator, and so it isn't immediately obvious whether the effect is predominantly one of facilitating evaporation or conflicting with it. So you'd have to look into that more deeply to understand the nature of the function, and that's not so important right now. That's something that you'll be able to play with later on when I show you a tool later in this video podcast. But the important thing is that delta is simply the slope of this curve, and those are the simple terms. It's essentially water vapor terms and temperature terms that are easy to measure. Okay, now the next thing we need to cover are the R's here. We have RS and RA, and in order to do that, I have to remind you that in the first video podcast, we defined the leaf area index, LAI, as the one-sided green leaf area per unit ground area. And we had this example from Africa. So I'm not going to go into it. If you don't remember, look back on video podcast 1 or Google, or look online. Okay, so now let's imagine an individual tree as pictured in this image here. So with an individual tree, you can imagine that if wind is blowing across towards that tree, that the tree is going to be blocking that wind. And then as that wind is moving through, there's going to be a lot of turbulence that's taking place as that causes mixing. So what this graph shows is the relationship between position in the tree as you go from the ground to the top of the tree and then beyond, above it, and the velocity of wind. So if we look at the y-axis first, 0.0 represents the ground surface, and 1 represents the top of the tree, which is pretty much illustrated with this photo here. So the y-axis is called the normalized height because z is just your altitude above the ground, h is the height of the tree or height of the canopy, and so z over h is the relative height. And this is one of the tricky things, is that a lot of things in the Penmen-Monteith equation related to the tree are all non-dimensional. That means whether this is a tiny leaf all the way, or tiny grass stalk all the way up to a vast tree, the ideas are intended to scale over that full range with no change in fundamental processes. So if we look within the canopy, which is the range from 0 to 1, we can see that along the x-axis is the velocity that's blowing across from left to right across here. The velocity, there's a certain velocity near the ground. At the ground, the air might be fairly open because there's not many branches and leaves near the ground. You just have the trunk. But then as you move up, you reach the thickest part of the canopy, and so the velocities are lower. And then as you head towards the top of the tree, velocities begin to increase because the canopy tends to be less dense. Now the exact shape of this profile, and higher velocities is further over to the right, lower velocities to the left. The shape of this profile is totally going to depend on the structure of each individual tree or the canopy composed of multiple trees, multiple species, and so on. So it's hard to say, but this is just the generic theoretical profile. Once you're above the tree, we take on what's called a logarithmic profile because the shape of this velocity function tends to follow the natural logarithm, and that's a basic principle in fluid mechanics if you look at flows over boundaries. There's two different curves here. One is for a low leaf area index and one is for a high value. For a low leaf area index, that means that there's more porosity, spaces in the tree, so you can get more air through. So you have higher velocities for the lower leaf area index, lower velocities for the high leaf area index, and then that crosses over above the tree. So these are the concepts. Now, how does this affect moisture? Well, wind obviously plays a large role in evaporation, and it does that for a very important reason. Because if air is sitting above a body of water or a tree that has water, the air can become saturated with water and then it can't take any more. If wind is blowing, wind can bring fresh air that's undersaturated and that can then continue the process of evaporation. So wind is important, but in order to have wind pick up air, it totally matters what the structure of that wind profile is, that really complex, turbulent wind. And it's not just a simple function of velocity. Like higher velocity means you're constantly bringing in fresher air, so stronger wind should yield a greater flux of water vapor, which means that there's a smaller resistance. So RA is aerodynamic resistance to evaporation. And so strong winds have, produce a small resistance. But it's not just about wind, it's also about turbulence, because turbulence stimulates mixing. And so simply by creating lots and lots of mixing, then you can also be spreading around that water vapor away from the leaves. And having more structure in here, like taller, more rough trees, can produce greater mixing and therefore a smaller aerodynamic resistance. So this is a good moment to say that resistance is the opposite of conductance or facilitation. So anything that helps evaporation, we might term conductance, like it helps it to happen, and anything that slows it down we could call resistance. So a high resistance should lead to reduced evaporation. So if I go back, notice that there is indeed an inverse relationship here between resistance and evaporation. Here it's tricky because we're in the denominator of the denominator, so but it's basically a scaling factor, so it's tricky. And you can play with this with a calculator later on in the video podcast. Okay, so if we go back to the Penmen-Monteith equation, how do we know what that aerodynamic resistance is? Well, you'd have to know something about what the wind pattern is. And unfortunately, wind patterns are not that simple. So the simplest we can do is say that the profile of wind moving through a tree canopy takes on this shape, and we can represent that using these logarithmic functions, as I mentioned before. One logarithmic function has to do with how the velocity in the canopy changes as a function of position up and down in the canopy for moisture, right, so this is momentum, so that's the wind, OM is for momentum, and then V is going to be for vapor. Notice that we have velocity, so the velocity, you could bring this to the left and say that the velocity through the canopy at any altitude Z above the ground is proportional to these logarithmic functions. In this case, we're not interested in the velocity, we're interested in the resistance. And so the resistance, therefore, is a function of these logarithms. So what's inside here? This is essentially asking how high are we above the canopy. So remember, this normalized height Z over H, essentially what we have here is Z over H. The fact that we have this little bit of a displacement taking place just recognizes that, where is the ground? On Earth, there is no true 0.00 because the ground is rocky. There could be shrubs there, or leaves. There could be all kinds of things taking place. And so this zero displacement helps to recognize that, not the zero, so the zero displacement recognizes that from the top of the tree, this logarithmic profile doesn't begin right at the top, but a little bit down into the canopy. And then the denominator here is this roughness length, which is what I was talking about, the roughness on the ground surface. Notice that all these variables can pretty much be converted to canopy height. So it's just blah, 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 constants, and then roughness, and then canopy height. So all you need to know is for any given elevation above the ground surface, how high is the tree or the canopy, and then the last thing is you have to know what the velocity is of the air that you're interested in. So all of this would allow for a prediction of what the aerodynamic resistance is, assuming this relatively ideal profile for what the velocity is doing in the air in and above the canopy. If anything deviates from that, it pretty much means you're out of luck and you'd have to go based on very complicated sets of field measurements, which would be a lot of work, but not infeasible, potentially. So typically, again, the Penmen-Monteith, it's an equation for estimating evaporation, or evapotranspiration, but it does have limits. Okay, and then finally, the last variable here, RS, this is the canopy or leaf or tree's resistance to wanting to give up its water. It has S here, meaning surface resistance, because the water is on the surface and those air pockets. Remember that from the Part 1 lecture. And so, the individual leaf has the ability to withhold its water from the air by closing those stomatal guard cells. And so you can imagine that this is going to be a function of many things, and a lot of effort has to go in to figuring out for the species of tree or crop that you're interested in what that surface resistance is. So now I'm going to show you some examples of functions for surface resistance. Okay, so this is for a forest in the United Kingdom. On the x-axis is the specific humidity deficit. Recall, specific humidity deficit is the difference between saturation vapor pressure and actual vapor pressure, so that's easy. The less moisture is in the air, the greater of a desire the air is going to have to get that water from the plant. And that means that the plant is going to have to mindfully stop that to the best of its ability from going away. And so as a result, you can see here that the tree actually has the ability to increase its resistance to giving up its water as the specific humidity deficit increases. Here's another example from Brazilian vegetation, the Caatinga tree in the lower right. Now, notice here the x-axis. Specific humidity deficit for Thetford forest was from 0, pretty much 2 to 8, and then the resistances were kind of like 80 to 240. So now we're at a much smaller vapor pressure deficit because obviously it's a lot moister in Brazil. So we're kind of going from 0 to 3 here, or 0 to 4. Most of these are ranging over similar numbers for surface resistance, like 50 to 250. And you can see there are some pretty tight relationships taking place until you get to the Caatinga tree. The Caatinga tree is shown here. You can see in this particular form, it's actually quite resistant. Look at the surface resistance, up to 7,000, 9,000. That's pretty strong resistance. One thing I should point out is the resistance has units of the inverse of velocity. So if, let's say that the vegetation is helping, it's like, here, take my water. If it's giving up the water, we call that conductance. So we can measure that conductance, that helping, in units of velocity, like meters per second. Since resistance is the inverse of helping, it's stopping it, then it has the units of 1 over velocity. Okay, here's another example. Surface resistance for wine grapes, table grapes, and mango orchards as a function of soil moisture. So the more moisture that's in the ground, the tree's like, hey, you can take my water because I can just go get some more, no problem. So the surface resistance goes down, pretty good relationships. Now let's look at the effect of leaf area index. As leaf area index goes up, there's more leaves. That means there's more pore spaces. That means there's more places for water to evaporate out of those pore spaces. And so therefore, the conductance is going up because there's just more leaves to give it off. So for an individual tree, higher leaf area index means that it's going to be able to give up more. If we compare the wet season versus the dry season, well, forgetting the fact that this is really bad science, that you should never report an R-squared when you only have 4 or 5 values. So just ignore that bad statistics. But nevertheless, if we just look at the overall concept here, during the wet season we have greater conductance, there's more water available, trees happy to give it up. During the dry season, conductance goes down. And so if the conductance is going up, then evaporation rates are going to go up too. This just helps to illustrate the variability of surface resistance. The lines in these plots show theoretical ideals that are used in computer simulations or computer models that are assumed. These are what are assumed. The dots here show some actual measurements measured through time, but just shown as a scatter plot. The upper left shows soil water storage. So in theory, the more soil water storage you have, then the greater the conductance should be. But notice here it's pretty much no difference. In general, we have in this particular study here, we see that the curve shows this trend, but there's really a lot of variability through time and so on for these other variables. So you should just think on your own, like, what is the effect of solar irradiance or time since dawn? What should that be? And then there's a lot of variability in the actual data. Speaking of variability through time, returning to our Brazil case, here are wine grape, table grape, mango, and Caatinga again. 2 growing season, on the left growing season 1, on the right growing season 2. The aerodynamic resistance is the dashed line, the canopy surface resistance is the solid line, and you can see how those values are varying through time. In some cases they're both relatively similar and showing the same results, but by the time you get to the Caatinga tree, you can see that the wind is doing one thing, but the canopy is doing something quite different. So the Caatinga really stands out. Okay, so as promised, I would like you to use some of your time to play with the Penmen-Monteith equation. One of the ways to do that is to use an online Penmen-Monteith calculator. These calculators come and go. I'm just showing you one, but feel free to just use your favorite web search engine and find one. But I've given you the address for one here. And you have to have Java enabled. When you do that, you can set values for the different variables and then see how the evaporation energy changes using the Penmen-Monteith equation. So this allows you to just change individual variables using the sliders and see what happens. So I encourage you to do that as an activity. How well does Penmen-Monteith work? Well, part of the problem is that it's pretty darn hard to measure evaporation over a canopy by other means. But what people can do is you can set up towers over it and then use that Bowen ratio method I mentioned before. If you look at the flux of water vapor and heat over the canopy using, like you have a big tower set up over the canopy and you measure those fluxes at 2 different elevations, as I said last time in part 1, you can estimate the evaporation with the Bowen ratio. And so this shows on the x-axis the measured flux and on the y-axis calculated in two different conditions with no stress or weak stress, and you can see that there is a pretty good relationship between the two, although there is also quite a bit of scatter. Now, when we look at a whole watershed, we have this significant problem because, if you look at this particular patch here, here's a mountain range. You see you've got clear cuts in here, you've got a lake, you've got snowpack, you have valleys and ridges at different angles to the sun and the wind. So it's actually quite complicated and very difficult to get that kind of watershed scale to regional scale flux estimate. But the Penmen-Monteith equation is widely used to get that. Here's an example where Penmen-Monteith equation was used for whole basins in Australia and compared to water balance estimate of evaporation, assuming that evaporation is the difference between gross precipitation and discharge coming out of that watershed. Now the problem with this is it's neglecting groundwater flux, so that's a factor. But since evaporation is the largest component, then it's sort of okay. And you see this quite commonly at the largest scales when people want to test things for evaporation. So on the y-axis is what's predicted with the Penmen-Monteith equation, and on the x-axis is the evaporation from the water balance. You can see that there's a strong relationship there, nearly 1-to-1, but there's also a lot of scatter. The last thing I want to talk about is a different perspective. So instead of trying to come up with one number that tells you for an individual tree, a canopy, a watershed, or even a region, one number for what that flux is for evaporation, another way to go would be to actually simulate the flux of wind, heat, and water vapor over the landscape. To do that, we turn to the idea of what's called the atmospheric boundary layer. So if we start at the ground surface here, we have these different zonations in the atmosphere. The surface layer is shown here. And so we can see that typically there's a specific humidity profile where moisture is decreasing and then changes abruptly. And meanwhile, there's also a profile in the temperature. So what we need to do is have a computer simulation that addresses that. And so there's a review article by Parlange et al. 1995 that I can refer you to that shows some of how this gets analyzed. There's also another analysis by Shaw and Schumann, which is showing some results here of how that would go. So what I'm showing here is across the x-axis distance horizontally, say over as you go across a field that has trees on it. On the y-axis is elevation scaled by tree height. So a value of 1, which is somewhere like here maybe, that would represent the height of the canopy. What you can see here are tiny little arrows, and these arrows are indicating that wind is blowing across from left to right, and some of these arrows are pointed down, which indicates that the wind is downwelling or pushing down, sweeping down. In other places it's going up. The lower plot shows the flux of temperature. Okay, and so what you see here is these solid line indicates contours of higher temperature, and then the dashed lines indicate contours of lower temperature. And you can see that there are bubbles of heat that are moving up as like a blob. Not a bubble, but more of like a blob of heated air that's moving up and lifting off. And you can imagine that in the same way, we can make a computer simulation to get water vapor. So what you see in these graphs, these are not real measurements, these are not data. These are computer simulation of the equations of motion for air blowing over the ground surface that has trees on it, and it can predict the spatial pattern if you took a slice across. We could also take the top of the tree canopy and do a horizontal slice and look down, like if you're opening up your head and looking inside. Here we're opening up the head of the canopy and looking inside, and the areas where you see solid lines are areas where you have higher temperatures rising up, and then so that would be like this whole side over here as well as some of these. And then the dashed lines would indicate cooler temperatures, which are places where flux is likely going down. And so you can see that there's a three-dimensional structure to wind, temperature, and then water vapor patterns that you can simulate. Obviously, this is far more complicated than just using the Penmen-Monteith equation, but it's a developing area that's relevant for ecohydrology in the future. Okay, so here are the references, and just to summarize, that this video podcast tried to present to you the Penmen-Monteith equation and explain the parameters that are in there. I highly encourage you to look at each term as I went through it, and on your own try to understand how that term is affecting evaporation on the whole. Use one of the online calculators and see how values are going up and down, and try to think about that relative to what I've said.